Hi friends, welcome to my channel PSU Aspirants. In this video, I am going to discuss boost converter from GATE and ESE exam questions point of view. In GATE syllabus, boost is the second DC to DC converter. So let's start with the boost, that is step up DC to DC converter. The circuit of the boost converter is as shown. Vs is the voltage source, DC voltage source connected to inductor in series with it. This is an inductor L. This inductor is connected with first switch S, which toggles at very high frequency Fs, and second is to the resistive DC load, that is R, through diode and capacitor in parallel with the load. This capacitor is used to remove the ripple in the output voltage or reduce the ripple in the output voltage. Now, the main functionality of this boost converter is because of this high frequency switching. So let's see what is occurring. This is the switch which becomes on or remains on for the time t on, and then it becomes off for the time t off. So let's see if the total time is t. Now t is equals to 1 upon f. F is the switching frequency. So duty cycle is the new parameter which is defined as t on upon t. So on time of the switch is dt and off time of the switch is total time minus on time. So t minus dt equals to t into 1 minus d. Now let's see the boost converter operation or equivalent circuit when the switch is on and when the switch is off. So first, when the switch is on, we can see here friends that in this parallel path the equivalent resistance is 0 because we are considering all the components as ideal. So all the inductor current will flow through this switch and current will not go through this part of the circuit, and it is isolated, this much part. So the on circuit can be given by Vs, Vl and switches. So we can see that inductors gets charged during the on period. Now off period or off period circuit we see, then whenever switch becomes off, so this inductor current which it built during the on time will starts flowing through this diode as the switch becomes off, and it gets passed through the diode. So the IL current flows through the diode and charges the DC load. So let's see the basic parameters from which GATE and ESE questions are asked, and it will help us to understand the boost converter completely. So first parameter is VL, voltage L across the inductor during switch is on and during switch is off. So friends, first voltage across the inductor can be given by V plus minus V minus. Now when the switch is on, so we can see that the voltage across the positive terminal is Vs and across the negative terminal is 0 because switch is idle. So on condition voltage is Vs minus 0 equal to Vs, which is positive in nature. Now for all DC to DC converter, the basic equation used to derive all these basic parameters are VL equals to L DelIL upon del T for inductor, and for capacitor is I C del Vc by dt. So we will use these equations only for all these parameters. So don't mug up the formula, just use this equation. You will immediately able to derive as I will derive in the video. So when VL is positive, so as the VL is positive, so we can see that del IL equals to VL into del T upon L. As VL is positive, the change in inductor current, this is del IL, will be positive. Hence the inductor current will rise from its previous value. So we can see this inductor current graph for boost converter. Whenever at t equals to 0, it was IL mean, and when at dt time it rose to one value called IL max, the change was positive as the voltage across the inductor is positive in nature. Now for off time, the voltage across the inductor we will see. For positive terminal it is Vs, and negative terminal of the inductor it is V0. This voltage directly is coming because diode drop is neglected, ideal case. So the voltage across the inductor is Vs minus V0. But I will soon prove that V0 will be always greater than the Vs. Hence, friends, we can see that Vs minus V0 will be negative because V0 is greater. So during off condition, voltage across inductor is negative. Hence, the change in inductor current during this time will be also negative. So current will decrease. So from time dt to t, the inductor current again decrease from its value IL max and back to its value of IL min. So let's start with second parameter, that is output voltage. For V0, we will use charging equation of the inductor, that is VL equals to L del IL upon del T. Second thing that is to be noted is the del IL. Del IL during the T on time will be difference of final inductor current minus initial inductor current. So it will be IL max minus IL min, and that is we can see from the graph as IL is increasing, so del IL will be positive. But in off time of the switch, the del IL will be IL min minus IL max, which will be negative because the inductor current is decreasing in nature during off time. So during on time voltage, this equation if we apply is VL is Vs equals to L into del IL upon time of on time. So on time is dt, and bringing dt this side we will get this equation Vs dt equals to L del IL. Now during the off time, the equation is VL is equal to Vs minus V0 is equals to L into del of IL. So del IL is negative during the off time period divided by off time. Off time is T into 1 minus D is equals to, bringing this T1 minus D this side, we will get this equation, that is number 2. Now from 1 and 2 we can see that L into del IL term is common. So we can equate these two like this. So solving this equation in which this T will be get cancelled, we will finally get V0 equals to Vs divided by 1 minus D, and that is the standard output voltage equation of the boost converter. Now let's see. Now we know that D is between 0 to 1. First consider D equals to 0. Output will be equal to Vs because D is 0. But as if we decrease the duty cycle or increase the duty cycle, so we can see that the output voltage will start increasing because 1 minus D would be less than 1, hence output voltage will increase. Hence this converter is called as step up converter also. Now another thing we have to note is V0 will be always greater than or equal to Vs for the boost converter. The third parameter is del IL. For finding the value of del IL, that is ripple in the inductor current or change in inductor current, we will use on time equation that we have derived earlier, that is Vs equals to del IL upon dt. So del IL ripple equals to Vs dt upon L. Now we know that 1 upon T equals to F. So we will use that in this formula. So we will get del IL equals to VSD upon FL. This is asked much in GATE or ESE exam. This based on del IL. So we can conclude that ripple in inductor current is inversely proportional to the switching frequency. As if we increase the frequency of switching, then ripple in inductor current will decrease. And second thing is del IL is inversely proportional to the inductor used. If we increase the inductor value in the boost converter, then ripple will reduce. The fourth parameter, that is average value of inductor current, maximum value of inductor current and minimum value of inductor current. So for deriving IL, we will use the capacitor current waveform, that is IC, for the on and off time. So let's look what happens during the on time. During on time, inductor current flows through the switch. Hence, the current that is delivered to the load is through the capacitor. Hence, the capacitor currents in this downward direction will be equals to minus I naught, because this I naught is delivered by the capacitor itself. Now, during off time, as the switch gets disconnected, the inductor current starts flowing through the diode into the load. So, the capacitor current will be equals to this IL current minus times of I naught current, that is gets subtracted from IL and is delivered to the load. Therefore, during off time, the capacitor current equals IL minus I naught. Now, for the stability of this capacitor, net charge gained by it, del QC, during a one complete cycle should be equal to 0. Otherwise, it will keep on gaining the charge and it will gain very high amount of energy. So, del QC is 0. Therefore, Q equals to I into T. So, del IC into T should be equals to 0. Therefore, IC on into T on plus IC off into T off must be equal to 0. So, we know that IC on equals to minus I naught. T on dt, IC off equals to IL minus I naught, and T off equals to T into 1 minus D equals to 0. From this equation, we will get I naught equals to IL into 1 minus D. And taking IL on the right hand side or left hand side, sorry, we will get IL equals to I naught upon 1 minus D. So friends, we have derived the inductor current in terms of load current. Now we know that I naught is equal to V naught upon R, which will be given in the question, value of resistance or directly the value of I naught. So we can get the value of inductor current from it using duty cycle. Now second thing is IL max. So from this waveform, the average value of this waveform is shown by this dotted line. We know that for the triangular waveform, the average value is exactly in center of its both extreme peaks, maximum and minimum. So if this is del IL, total difference, then this above part will be del IL by 2 and the below part will also be del IL by 2. So from that we can get IL max equals to IL plus del IL by 2 and IL mean equals to IL minus del IL by 2. Another thing that is to be noted, we have derived the formula for ripple in the inductor current is equals to dVs upon FL, and that if we substitute in this equation, we can get the value of IL max and IL mean both. Now another thing I want to focus is, as we know, del IL is inversely proportional to the value of the inductor used. So if we, in questions, most of the GATE questions or ESE, it is given that consider very high value of inductor so that ripple is assumed to be 0. Because high, so as L is high, so del IL will be tending to 0. Hence the inductor current waveform will look like something like this straight line which I have drawn in this third graph. Okay, and this is the capacitor current waveform which I have drawn in the middle. IC equals to minus I naught for on time and equals to IL minus I naught for the T of time. Now IL is the average. Second thing I would like to say, if we want to simply just by observation we have to derive the value of IL in terms of I naught. It's a short trick. We can see that whenever this switch is on, IL flows through the switch, it does not goes to the load. But whenever it gets on, as soon as it gets switch gets off, the IL flows through the load. So IL flows only for the off time, which is proportional to the 1 minus D duty cycle. So we can directly get this I naught equals to IL into 1 minus D times only. If this is average value of I naught and this is average value of IL, therefore TT gets cancelled in numerator and denominator. That's why the I naught average equals to IL into 1 minus dt upon T. So TT will get cancelled and we can directly get this equation that I naught equals to IL 1 minus D. That is a short trick used. So let's start with the fifth parameter, that is source current. Now we can see that this source and inductor are connected in series without any another switch or diode between them. So whatever the source current which is going to be delivered is equal to the inductor current because of series connection. Therefore, Is equal to IL, and the waveform also we can see here. The IL as was the IL waveform, same waveform is of the Is for 0 to T. And the value of IL is equal to I naught upon 1 minus D. So Is is equal to IL, same. The sixth parameter, I switch, average and RMS value will derive using the thing or concept is that whenever the switch is on, the inductor current flows through the switch. But as soon as switch becomes off, inductor current do not flow through the switch. So the switch current waveform can be denoted by for 0 to dt, it has value same as IL, but for time dt to t, it has value 0. Hence the RMS value and average value we will calculate. So the first thing is the average value ISW. The ISW equals to IL into T on upon T. That will be equal to dt into upon T into IL. So TT will be cancelled. So we will get IL into D. Now the second thing is the I switch RMS value in terms of the inductor current, that can be given as root of IL square into T on upon T. So it will be equal to IL square dt upon T. It will get cancelled and we will get I switch RMS equal to IL into root D. So seventh parameter is ID, diode current, average and RMS value. You can see that whenever the switch is closed, no inductor current flows through the diode as complete inductor currents get passed through switch. But when the switch is turned off, inductor current flows through the diode into the load. So the diode current waveform can be drawn like this. For on time, inductor current will flow through the switch. So the diode current will be 0. But for the off time, complete inductor current will flow through the diode. So now we will derive the average and RMS value of diode current in terms of inductor current. So first is average value of the diode current will be IL into time for which it is flowing, that is T of divided by total time period. So IL into T1 minus D upon T. This will get cancelled and we will get diode current equals to IL into 1 minus D average value. Second thing is RMS diode current, that will be IL square T off upon T's root, whole root. That will be equal to final value of diode RMS current will be IL into root of 1 minus D. This values is same as the buck converter that we have derived in the previous video. Now we will see the 8th parameter, that is del V naught, ripple in the output voltage. So the output voltage is appeared across the load with the help of capacitor. Now we will use the charging equation of the capacitor IC equals to C del Vc upon del T to find the ripple in the voltage due to the capacitor. So IC for on time we have derived was equal to minus I naught is equals to C into, now we have to see that during this time whenever the circuit is on, this portion of the circuit is isolated from this source because the inductor current flows through the switch. Therefore, this capacitor supplies the current to the DC load R. Therefore, capacitor discharges. Hence, the voltage across it is decreasing in nature. Therefore, del Vc equals to minus del V naught divided by dt for the time interval, on time interval. Therefore, del V naught is equals to I naught d upon Fc because 1 upon T I have taken as F. Now, for maximum del V naught, duty cycle will be d equals to 1 because del V naught is directly proportional to d. One important thing we will note now, as we have noted in DelIL, that del V naught is inversely proportional to C. Similar to the case of del IL is inversely proportional to L. Let's start with the 10th parameter, that is L critical. So let's see what is critical inductance. So this is the graph of inductor current versus time. So first of all, for the normal value of L1 inductance, this is the graph of IL versus T. But suppose if I decrease the value of inductance to L2. So let's see what is the effect. For we know that del IL, ripple in inductor current, is inversely proportional to L. So by decreasing the inductance, ripple should increase. Hence, for L1 this was the graph. For L2 the graph shifted below. Its minimum value shifted below so that the ripple can increase. Previously it was this much, but now as the graph has shifted below, minimum value has shifted below, so ripple has increased. For further decrease in inductance to some value L crit, the graph shifts below to such a value so that this L crit, third graph L crit, the minimum value of inductance such that the minimum value of current becomes 0 at the end of the time period. So such value of critical inductance for which IL min becomes 0 is called as critical inductance. For inductance less than critical value, this graph is fourth one, L4. You can see that the current becomes 0 before the end of the time t. So for L4, the mode is called as the discontinuous mode. L, for any value of inductance less than the critical value, the mode becomes discontinuous, and for L greater than or equal to critical inductance, the mode is called as continuous mode. So questions are asked very much based on discontinuous and continuous mode differentiation. So we should know how to differentiate between these two modes. So now IL min is 0. So IL min is IL minus del IL by 2 equal to 0. The IL equals to del IL by 2. Therefore, substituting del IL, dVs upon FL, and IL is equal to I naught upon 1 minus D. But we know that I naught is V naught by R. But V naught is equals to Vs upon 1 minus D. We derived in second point. So Vs upon R into 1 minus D whole square is equal to dVs upon 2FL. Therefore, from that we get L. In this case is LC because it is the case for IL min equals to 0. So L will be, in this case will be LC. So L critical or LC is equal to R 1 minus D whole square into D upon 2F for boost converter. Now, if we compare it with the derived in buck converter, L crit boost is equal to L crit buck into D into 1 minus D. Because for buck it was R into 1 minus D upon 2F. So let's start with the 11th parameter, that is C critical. For C critical, similarly Vc min equal to 0. Therefore Vc minus del Vc by 2 equals to 0. So Vc equals to del Vc by 2. But Vc equals to capacitor voltage equal to V0. So V0 equals to del Vc by 2. Now substituting del Vc equals to del V0 derived previously equals to I0 dt upon Cc. Cc denotes critical capacitance equals the from that V0 and this I0 is V0 by R. So V0 get cancelled. So we get finally C critical capacitance Cc equals to D upon 2Fr. Let's start with the summary at the end. So first parameter was VL. For switch on, VL was equal to source voltage, and for switch off condition, it was equal to Vs minus V0. For switch on, it was positive in nature, inductor voltage VL, so inductor current was increasing. And for switch off, it was negative, so inductor current is decreasing in nature. Second thing is output voltage is equal to Vs upon 1 minus D, and that's why name is given boost converter, because V0 is always greater than or equal to Vs. Third thing was ripple in inductor current is equals to dVs upon FL. Fourth thing was the IL. Now we derived the IL in terms of I0, that is equals to I0 upon 1 minus D, and use for calculation of remaining these parameters. So IL max equals to IL plus del IL by 2, and IL min is equals to IL minus of del IL by 2. And IS is equal to IL. I switch current is equal to IL into D, average value, and RMS value is equals to IL into root D. I diode current is equals to IL into 1 minus D, average value, and RMS value is equals to IL into root of 1 minus D. Eighth thing was the ripple in the output voltage, that is equals to I0 D upon FC, and condition for maximum ripple was duty cycle D equal to 1. 10th thing was the critical value of inductance for the boost converter is equals to R into 1 minus D whole square into D upon 2F, and is in terms of buck converter, if we want to write, then equals to LC buck into D into 1 minus D. And for L greater than critical value, mode is continuous, and for L less than critical value of inductance, the mode is discontinuous. C critical for the boost converter was given by D upon 2FR. Now friends, at the end I would like to tell you, do not mug up any of this formula, just learn the procedure to derive them both in buck, boost, and now upcoming buck boost converter. Also, please take the snapshot of these parameters and add it to your short notes. If you have any doubts or queries, you can write in the comments or send me email directly in the description link given below. Please like this video and subscribe to my channel PSU Aspirants. Thank you.